Today, we're going to pull back the curtain on a kind of hidden magic in the world of software. We're talking about the art of laziness and how something called a compiler uses it to make all the code we use every single day just a little bit faster.
So let's just start with a question. What if the smartest way to work, the most efficient way to get something done, was to be just a little bit lazy?
To see what I mean, let's actually step away from the computer for a second. Just picture this. You're in the kitchen, you're baking a cake, and the recipe calls for 2 cups of sugar.
Okay, so you need 1 cup for the actual cake batter.
And you're going to need that 2nd cup later on for the frosting.
All right, so here's the question. Are you going to measure out 1 cup, dump it in the batter, wash the measuring cup, put it away, and then pull it out all over again just to measure that 2nd cup for the frosting? No way, right? Of course not. You do that little bit of work once. It's just smarter.
Well, that simple idea, the idea of not doing the exact same work twice, that is precisely what happens deep inside our computers billions of times a second. So let's bridge that gap from recipes to programs.
Okay, so what you're seeing here is the cover of the legendary Dragon book. It's pretty much the Bible for a tool called a compiler. And what is a compiler? Well, you can think of it like a translator. It takes the code that we humans write, in languages we can actually read, and translates it into the fundamental ones and zeros that a computer processor can actually understand. And it just so happens compilers are absolute experts at not measuring the sugar twice.
See, when a programmer writes just a single line of code, something simple like show this picture on the screen, that's written in what we call a high-level language. It's easy for us to read. But for the computer to actually do it, that one line has to be broken down by the compiler into dozens, maybe even hundreds of tiny, super basic steps. And this process, this expansion, it naturally creates repetition. The same little calculations just pop up over and over again. And here's the key part. As programmers, we don't even see this happening. It's all under the hood. The compiler is like the silent, helpful assistant that goes through, finds all that hidden repetition, and just cleans it up for us before the program even starts.
So you might be wondering, how does a compiler even spot this extra work? Well, it's been taught to recognize a few distinct patterns of repetition. We can kind of break these down into 3 main types, each one getting a little more clever. We've got the obvious repeats, then the hidden repeats, and finally, the really interesting ones, the tricky repeats. All right, first up, the obvious stuff. Let's say the calculation b plus c. That's our 1 cup of sugar. Now, look at the code on the right. The program is asked to calculate b plus c here, and then later on it's asked to do the exact same thing again. The compiler spots this immediately, so it does what you see on the right. It calculates b plus c just 1 time, saves the answer in a temporary variable, we'll call it t, and then it just reuses t whenever it needs that result. Super simple, but really effective.
Okay, next up, hidden repeats. This one's a little sneakier. Look at this calculation, y times z. It's stuck inside a loop that's going to run 100 times, but the compiler is smart enough to notice that y and z don't actually change inside that loop. So the result of y times z is going to be the exact same every single time. Instead of doing that math 100 times, the compiler just lifts it right out of the loop, it does the math once, stores the answer, and then just uses the answer inside. It's literally measuring the sugar before you even start mixing the batter.
But that brings us to the trickiest problem of all. This is where the real cleverness comes in. What happens when a calculation is repeated, but only sometimes? Only on some of the paths the program might take?
Let's look at this flowchart as a kind of map of the program's logic. Okay, now imagine the program takes this top path. It flows through here, does the calculation b plus c, then it goes through the next block, and when it gets to the end, it does b plus c all over again. That's a classic repeat. It's wasted work.
Okay, but what if things go differently? What if the program takes this other path, the bottom one? Notice on this route that b plus c calculation, it doesn't happen. So when we arrive at that final block, we actually need to do the math. It's not a repeat on this path. This is what's called partial redundancy, because the work is only extra on some paths, but not all of them.
And this creates a really interesting puzzle, right? You can't just get rid of the calculation at the end because that bottom path needs it. But you can't just move it to the very beginning either because that might mess other things up. So where in the world do you put the calculation so that it happens exactly once, no matter which path the program takes?
Well, the solution to this puzzle is a beautifully elegant technique, and it has a fantastic name, lazy code motion. So what is lazy code motion? It's all about finding the perfect moment to do the work. The core idea is this. You postpone the calculation. You do it at the absolute latest possible moment where you can still guarantee it won't be repeated. Why wait? Well, by waiting until the last second, the compiler doesn't have to hold on to the answer in memory for very long. It's not just lazy, it's efficiently lazy.
So check this out. Here's what the compiler actually does. It's amazing. It doesn't just move the code, it redraws the map. It surgically inserts a brand new little block right here, only on the path that was missing the calculation. And just like that, the puzzle is solved. Now, no matter which way the program goes, the calculation is performed exactly once before it gets to the end. The partial redundancy is totally gone. It's just an incredibly clever solution.
Okay, so let's just zoom out for a second and appreciate what's really going on here. This is like a hidden art form, working silently inside our machines all the time. You know, the authors of that Dragon book really put it perfectly. They say that by letting the compiler handle all these little redundancies, we get the best of both worlds. We, as programmers, can focus on writing code that's clear and easy to understand, and we can trust the compiler to go in and make it ruthlessly efficient for the computer to run.
And you have to remember, this isn't some abstract theory. This silent, clever work is happening constantly, right now. It's happening inside the browser you're using to watch this. It's happening in the apps on your phone, in your computer's operating system. It is one of the deep, foundational reasons our digital world is as fast and responsive as it is.
And that really brings us right back to where we started. True efficiency, whether it's in code or just in life, it isn't always about working harder. Sometimes it's about finding that one simple, elegant, and maybe even perfectly lazy idea that does all the heavy lifting for you.